In this video, I wanted to discuss what is an Euler path in an Euler circuit, or as the second video that I showed you earlier in this lecture, they refer to as an Euler sweep, or sweeping is kind of the same idea as a circuit. And this is another super important term, which is why I'm making it into its own video. But an Euler path is a path that covers all the edges of the graph. So again, it has the same connotation as the term path, to which I was mentioning. But notice, like basically, it's a complete circuit, or sorry, a complete path, which has to cover every single edge. Also, it's important that deadheading is not allowed because that was built into the definition of what a path was. And same goes for a circuit. An Euler circuit is a circuit that covers all the edges of a graph, again, assuming no deadheading. And this is the typical goal of this chapter when we're solving a street routing problem. Typically, the goal is to find either an Euler path or an Euler circuit because it's all about completionism. Right? If we're returning back to the very initial example, it asks us, we were a security guard company and we were trying to patrol the entire neighborhood, beginning here and returning back to the starting point. So as we were trying to patrol these neighborhood, our goal was to develop an Euler circuit, basically hit every edge, return back to the start, and thinking about, is there an optimal way to do it? So that's what an Euler circuit would be an optimal sweep of the entire neighborhood. And so what I wanted to mention is sometimes it's not possible to find Euler circuits and Euler paths. Sometimes it is. And that is exactly a lot of that. That's the math that Leonhard Euler did back 300 years ago. And he's a very famous mathematician. He's actually my favorite mathematician. Not for this math, but for a lot of other math. He was very vital in the notation, the development of mathematical notation, which we still use a lot of his way of doing math today. But anyways, like in this particular graph, sometimes it's not possible to find an Euler circuit. So we could, like, before we talk about like the mathematics of determining how to find Euler paths and Euler circuits, let's just say we're trying to find it just by guessing. Like for example, we could try to go like this, and like if we were thinking about an Euler circuit, again, it would have to be a circuit which returns back to the start and would have to hit every single edge. But as I said before, if we're trying to hit every single edge in a graph that has a bridge, we're going to run into a problem because as we're covering all the edges, we get stuck because we've already used this edge. And that's the huge problem in these chapters, is what happens when we run into an edge we've already used. And also notice that there's other edges I've missed. How do I go back and cover those if I'm not allowed to deadheading? And that's why some graphs do not have Euler circuits. And in these sorts of problems, we shouldn't give up and stop working, but there is a way of solving them, which is what we refer to as Eulerizing. And we'll talk about that in 5.4. But also thinking about an Euler path, say for example we wanted to start at A and end at K, you might think, well, maybe we could actually do that too. That would be where we'd have to hit every edge and try to end up at a particular point. We might run into the same problem with how do I start at this point and end at this other point while using every edge without leaving off some of them. And basically, we don't want to have to guess. Instead of guessing, that's what we're talking about. We're going to examine the math behind these. And the way that your textbook will often describe Euler paths and circuits in graphical form is one way, but notice like they provided a couple examples of cases where they had an Euler circuit and Euler path. And how you want to read this is by following along the arrows in the numbers. So in figure 5.9, it says an Euler path starts at C and ends at D. So if we start at C and follow along, notice it says 1, 2, 3, 4, 5, 6, 7, 8. Notice that like in doing that path, we hit every edge of the graph as we're traveling, and we did not deadhead at all. And so sometimes certain graphs is possible to have an Euler path, and that one would be a path because it started at C and ended at D. Whereas some graphs may have an Euler circuit instead. Here they have not numbered them, but say we started at C in the same way. If we're trying to find an Euler circuit, we'd be starting and ending at the same point. So if we would start at C, we should come back and end at C as well. So I'll go ahead and highlight it just so we can keep track. Let's say we did that step 1, step 2, step 3, step 4, step 5, 6, step 6, step 7, step 8, step 9, step 10. Notice that we can completely traverse this graph. Again, no deadheading, it worked, and we started and ended at the same point, and which would give us an idea of what an Euler circuit would look like. But in other graphs, sometimes neither would be possible. Like say I was trying to have an Euler circuit starting at A, I could try to go to D first, C, B, D. But again, we run into the problem where I'm going to get stuck because there are edges that have been left off. And again, we're not allowed to deadhead. And that's exactly the issue with these problems. And similarly, there would be no Euler circuit in this problem either. And it turns out that Leonhard Euler figured these things out in the 1700s, and solve these problems. And if you're wondering how would a person ever think of all this math and determine these things, I want to talk about how he sort of thought about it and what triggered his ability to think about this. And then we'll kind of return to how we apply this to those street routing problems that we're trying to solve. So basically, if we want to determine if a graph has an Euler path or an Euler circuit, like in this last example, it told us, okay, these graphs have an Euler path. These graphs have an Euler circuit. How would we know that? And that's exactly what Euler's circuit and Euler's path theorem state. I'll go ahead and read them out loud. I also want to talk about, well, why are these theorems true in as basic of a manner as possible. But Euler's circuit theorem states that if a graph is connected and every vertex is even, then it has an Euler circuit. If it has any odd vertices, it does not have an Euler circuit. So let's focus on that. It has to first be connected, and that's kind of an obvious thing, because if it's not connected, there's no way that you can cover every edge, because they're not connected. So we're assuming that our graph is connected from the very first part. But notice the second condition, this is what is really important. If every vertex is even, then it has an Euler circuit. So it's very direct. If they're all even, it will have an Euler circuit. If it has any odd vertices, then it does not have an Euler circuit. And if we go back and look at the previous example and kind of focus on the graph that we were looking at, notice that in this graph it said it had an Euler circuit. If we go back and really examine the vertices closely, vertex F was degree 2, even. D, degree 4, even, 4, 4, 4, and E, 2. Notice that every vertex here was even, and that helps us to explain, well, why did it have an Euler circuit? How would I have known this? And it's basically a very simple process. And notice that what it said is that if it has any odd vertices, it does not have an Euler circuit. Like over here, notice that each of these vertices are degree 3. And for some reason, there's no dot here. I don't know why. That must have gotten deleted on accident. But notice every vertex here, odd, no Euler circuit possible. And over here, notice that vertex C and D were both odd. No Euler circuit either. Notice that this did not specify that it did not have an Euler circuit, but upon inspection, we know that it cannot due to Euler's circuit theorem. And there's a very similar theorem for Euler paths, which is pretty much just as easy if you're focusing on the conditions. So it says if a graph is connected and has exactly 2 odd vertices, then it has at least one Euler path. It also says that any such path must start at one odd vertex and end at the other, which is not an important thing to overlook. And then if a graph has more than 2 odd vertices, it cannot have an Euler path, or technically 0 as well. It can't have an Euler path. I don't know why that wasn't stated in the theorem as well. Also, just before we go back and look at Euler path examples, I wanted to mention, what does the term theorem mean in math? And the basic idea is a theorem is like a statement. It's a rule. It's something that is for sure true. But if you're wondering, well, why? A theorem is something that mathematicians must prove rigorously. And this was part of the thing that Euler did. He proved that this stuff is 100% true no matter what, using mathematical stuff. And in the field of graph theory, a lot of what you do is you're going to prove these sorts of things. Now, I'm never going to ask you to prove that this is true, because that's a little bit more technical and gets into the know-how. But I do want to explain, well, why, as we wrap up this video. Because there's always an idea behind them in terms of, well, what is the pattern and how do I isolate what's critical to these patterns? But basically, you can kind of close the book on this if it has, in the determining whether graphs have circuits or paths, or Euler circuits or Euler paths, is solved. And that's what these theorems describe. And returning back to this, notice that in graph 5.9, figure 5.9, it had exactly two odd vertices, C and D. Hence, it has an Euler path that must start at one of those and end at the other. And if we go back and look at that, that's exactly what happened, right? We started here, went like this. It started at C, ended at D, and it follows exactly what Euler's path theorem said exactly. And this graph has no Euler path because it had more than two odds. It said it had to have exactly two odds to have an Euler path. And this one also will not have an Euler path because it had no odds. It was completely even. So notice a graph can either have an Euler circuit, or it can have an Euler path, or it can have neither. And to synthesize all this information, it all has to do with, does it have 0, does it have 2, or does it have more? If it has 0, it has an Euler circuit. If it has 2 odds, it has an Euler path. If it has more odds, it can't have either. And that's it. And you might be thinking to yourself, well, what if it has 1 odd? Then what? Because that's not explained in any of these cases. Actually, it's impossible for it to have 1 odd by other theorems, which I'll talk about in another video, because this one is getting quite long. But before we end this one up, I wanted to explain, well, why are Euler's circuit and path theorems true? So let me move back to the whiteboard for a second, because it's hard to explain these things without a graph or without being able to draw. And so I wanted to illustrate why Euler's circuit and path theorems made sense to begin with. So let's start with Euler's circuit theorem, which, as I already discussed, said that if every vertex is even, then it has an Euler circuit. So really, it's all about why is evenness important and why is oddness bad. And one of the ways I like to say it in class is even is kind of good and odd is bad, and that for street routing problems. And if we think about the case where we have an even layout, or all the cases to which we have an even degree, or even up to 6. So imagine that in our graph, and this is technically, these would not be proper graphs because each edge, as I said, has to have a dot at the end. But I'm just focusing on what does a degree 2 vertex or degree 4 or degree 6 vertex look like when they are even. And notice that if I'm thinking about being a completionist here, where I'm trying to find an Euler path, the goal is to hit every edge in the graph. And if I think about traversing along an even graph, like when it's degree 2, I kind of can go in and out of that vertex. And I have no problem in traversing every edge in that immediate vicinity. So that vertex does not really create any problems. Or if, say, I was thinking about a degree 4 vertex, I can kind of go in and out. And then, as I'm traversing through the rest of my graph, I'm going to have to hit every edge to be an Euler path or circuit. So I'm going to have to come back through it later. But notice that, when it's degree 4, I go in and out, in and out. And that whole in and out pairing is an even pairing, which is why evenness is so important. When it's even, or even degree 6, notice I go in and out, in and out, in and out. I don't get stuck anywhere. It's very nice for flowing and traveling. Now, this is the whole problem with odd vertices and why, when a graph has any odd vertices, it won't have a circuit, or if it has too many, it won't have a path either. Because if I'm thinking about oddness, say for example, well, obviously a degree 1 vertex would be odd, as would degree 3, like that, or say for example degree 5, just say like that. And let's see kind of why these are problems. Well, if I think about a street routing problem, well, a degree 1 vertex would be very much like a dead end, right? A lot of times you have a cul-de-sac and the street just ends. And if I'm going in to deliver packages or patrol that neighborhood, obviously I run into a dead end. And what do I have to do? I have to turn around and go back out, which technically is deadheading. And you might think of it, well, is that really deadheading? Because there's no other option. But in the graph theory sense, yes, because if I'm running into a dead end, that's it. I'm not allowed to reuse an edge based on the definition of a path or circuit. So, we run into that problem with degree 1, obviously. And same with degree 3, if I'm going in and out of that vertex. Well, eventually, if I'm trying to hit every edge and, completely do a complete sweep, I'm going to return back. I have to return back to this edge at some point, and I would have to come back in from another location. And I'm going to get stuck at that location due to the fact that that's odd. Because again, technically I have to leave, but I'm out of edges, and I go in and out, in, and I get stuck. And same with degree 5, in and out, in and out, in. At some point I'm going to get stuck. And every odd vertex in a graph is like a hinge, or it's a point in which you're going to get stuck. And that's why these theorems make sense. And returning back to the example with the bridge, if we go back and look, well, do these graphs have Euler circuits or Euler paths? Notice that if we focus on all of the odd vertices in those graphs, which we have, what I like to do typically is circle them in red. We had an odd vertex there, 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 and there. Notice that there are 6 total odd vertices, so it will have neither an Euler path nor a circuit due to that reason. Let's go ahead and wrap this video up, and we'll do more examples in the next video.